Part A loudspeaker oscillates with frequency f to produce sound waves of wavelength lambda. So we have given the value of frequency and the wavelength of the sound. The loudspeaker makes n number of oscillations in time. So n number of oscillations in time t. So we know that frequency is equal to number of oscillations per unit time. So number of oscillations per unit time. So n number of oscillations and time. So state expressions in terms of some or all the symbols f, lambda and n for the distance moved by a wavefront in the time t. So that distance moved by a wavefront. So basically we need to just calculate the distance moved. So what is the distance? So distance is the number of waves produced and the lambda. That is, lambda is the wavelength for one wave. So the wavelength for one wave into number of waves, that is n. So n is the number of oscillations. So the loudspeaker makes this much oscillations. So this much waves must be produced, and so this much waves must be produced, and each wave has a length of lambda. So the total length or the total distance is n lambda. That is, number of waves into wavelength is the total distance moved. So the time t. So time t. So we know that frequency is equal to number of oscillations by time. So time is equal to n by f. That is n by f. And also frequency is 1 by time period. That is, the time period is the time for one wave, and one mentions that it is one wave. But there are n means many waves, and the time is the time for many waves. So if we just divide, then we will get this much value, or the time for one wave. That is, frequency is equal to number of oscillations per unit time. Frequency is equal to number of oscillations per unit time. Similarly, frequency is equal to number of oscillations. Here we consider the oscillation as one oscillation and the time as a time for one oscillation. Use your answer in A1 to reduce the equation relating the speed of the sound to frequency and lambda. So we need to relate speed with frequency and lambda. So we know that V is equal to, since we need to relate this, so initially we don't know that V is equal to f lambda in this form. But we need to show that V is equal to f lambda, or we have to find that V is equal to f lambda. So initially we need to relate this. So now initially we know the equation, that is velocity is equal to distance by time. And since we know we must use our answers from A1. So we know the distance and we know the time. So we know that velocity is equal to distance by time, or velocity or speed is equal to distance by time. So the distance is n lambda, that is n lambda, by time, that is n by f. So n and n cancels and f comes above, so it will be n lambda or lambda f. Lambda f, yes, it is lambda f. So distance, that is n lambda, by time, that is n by f, and since it is divided, so it comes above. So n and n cancels and the final equation becomes n lambda. So we relate V in terms of f and lambda. Then the wavefront of a sound wave is displayed on the screen of a cathode ray oscilloscope as shown in figure 5.1. So the wave is shown in the cathode ray oscilloscope. The time base is 0.20 millisecond per centimeter. So the time base, or the time for one box, is 0.20 millisecond. So the time base setting, so yes, the time for one box is given. Determine the frequency of the sound. So we know that frequency is equal to number of oscillations per unit time. So we consider the oscillation of the wave produced as one wave. So frequency is equal to 1 by time period. That is, for one wave, frequency is equal to 1 by time period. So 1 by the time period. So what is the time period? Time period is the time taken for the wave to complete. So 1 box, 2 box, 3, 4. So here we can see that the complete wave is formed in 4 boxes. So the time period would be 0.20, and we have to remember that this is millisecond. So milli is 10 to the power minus 3. 10 to the power minus 3. So 0.20 10 to the power minus 3. And since this time base is for one box, but the total wave is completed for 4 box, so this value into 4. So 1 by time period, we get the frequency as 1250, or approximately 1300, to two significant figures. For part C, two sources S1 and S2 of sound waves are positioned so that as shown in figure 5.2. So this is the source of sound. That is, these two are the source of sound, or the source of sound that produces sound. The sources emit coherent waves. So coherent sound waves. Coherent means that the waves have a constant phase difference. So coherent means constant phase difference between the waves. Coherent means constant phase difference between the waves. So coherent sound waves of wavelength lambda. So we get the value of lambda. A sound detector is moved parallel to the line S1, S2 from position X to position Y. So from position X to position Y, a sound detector is moved that can detect the sound. Alternate positions of maximum loudness L and the minimum loudness Q are detected as illustrated in figure 5.2. So where constitutive interference occurs, loud sound is produced or maximum amplitude is produced, and where destructive interference occurs, quiet sound or minimum amplitude is produced. So here constitutive and destructive interference occurs. Now distance s1x is equal to the distance s2x, distance s2x, distance x2x, distance s2y is 1.40 meter. So s2y is 0.70 meter as given. So explain what is meant by coherent waves. Coherent waves means that the waves have a constant phase difference between the waves. So the waves must have a constant phase difference between the waves. So state the phase difference between the two waves arriving at the position of minimum loudness Q that is closest to point X. So first of all, what is point X? Now S1 and S2 emit sound, and for position X, so this is the center of S1 and S2. So position X, here we can see that position X is the central maximum amplitude. So position X is the central maximum amplitude, or it is the central position of maximum amplitude. So this is the center between these 2 points, between the 2 sources, or the central maximum amplitude. Now from that is closest to point X, state the phase difference between the two waves arriving at the position of minimum loudness Q. So arriving at the point of minimum loudness Q, so it is mentioned that Q is the minimum loudness, Q is the minimum loudness. So at the position of minimum loudness Q that is closest to point X. So which Q is closest to X? So which value of Q is closest to X? So this value of Q is closest to X. Now we need to find the phase difference between the two positions. So initially at the central maximum amplitude, this is 0 lambda. Then the phase difference would be, at the waves arriving at this point is 0 lambda. So this is the, or we can say that this is the path difference. Path difference, and for the phase difference, so the waves arriving at this point has a path difference of 0 lambda and a phase difference of 0. Then for next maximum, that is the next maximum or next loud, it would be path difference of 1 lambda and the phase difference of 360 degree. Then for the other loud or the other maximum, so 1 maximum then 2 maximum, since it is 360 degree, so the other maximum must be 720 degree and the path difference would be lambda. Similar to that, and here constitutive interference occurs. So constitutive interference occurs, and due to this constitutive interference, maximum amplitudes are produced. Now for the destructive interference, so for destructive interference, that is for the quiet sound, so this is for the loud sound, and for quiet sound destructive interference occurs. So destructive interference occurs for quiet sound, and for quiet sound from the central maximum wavelength or central maximum, so from the center, this is the closest quiet sound. So here the path difference from loud to loud is 1 lambda. So from loud to quiet would be lambda by 2. Similar to this, for the next quiet, since loud to loud is 2 lambda, so 1 lambda and lambda by 2. So this would be 3 lambda by 2. That is the path difference. And what is the phase difference? Phase difference would be 180 degree for distributive interference. Since for constitutive interference, we consider the path difference as 360 degree. So this would be 180 degree. And similar to this, for this quiet sound, that is at this position, the quiet sound or the distributive interference occurs. So 360 degree from loud to loud, and then from the next loud to the quiet. So loud to loud is 360 degree, and from this loud to this quiet is 180 degree. So in total, what is the phase difference? So the phase difference in total, we can say that it is 360 plus 180. That is 520 degree, 540 degree, 540 degree. So from the central maximum or central loud to this quiet, that is 360 plus 180, that is 540. Now, what is our question? This question asks us to find from the central maximum, that is x, to the closest q. So what is the closest q? So this is the closest q. And so for this closest q, we know that for q it is distributive interference. So the phase difference, the path difference would be lambda by 2. Since the path difference between loud and loud is lambda, so loud and quiet must be lambda by 2. And what is the phase difference? So for loud and loud, the phase difference is 360 degree. So for loud and quiet, the phase difference would be 180 degree. So what is the phase difference? It is 180 degree for this distributive interference. Since here we can see that distributive interference occurs. So for loud to quiet or maximum to minimum, distributive interference, and from maximum to maximum, constitutive interference. Now, for the next part, determine the distance S1y. So we need to find the distance S1y. So we need to calculate this value of distance. So what would be this distance? Now you need to read the question carefully again. And here we can say that S1x equal to S2x. So that means S2x, that so S2x. So need to relate the lengths to solve the problem. Now the basic thing is that from loudness to loudness, the distance that we get is equal to the loudness to loudness, the distance that we get. Similar to that, from one quiet to the next quiet is one quiet to one loud is the equal distance as one loud to one quiet. This is an obvious thing. Now, distance S1x. So first of all, the information that we have given, the distance S1x. So S1 and x equals to the distance S2x. So S2 and x. So this distance is equal to this distance. Now what is distance S2x? So for distance S2x, now this is the baseline. Here we can see that this is the baseline. So the baseline, so from this loudness to this loudness, this is one distance or one lambda. Similar to this loudness to this loudness, this is also one lambda. So that means here we can see that from the baseline, this length is also equal to this length. So from the baseline or from the right angle triangles, here we can see that this length is equal to this length. That means if this is 7.40, then this would be 7.40. And we know that S2x is equal to S1x. So S1x must also be 7.40. So S1 to x is 7.40 and 7.40, and we need to find S1. So we need to find S1y. So what would be S1y? So we need to find S1y, that is this distance S1y. So S1y would be S1x, that is this distance, plus this distance. So here we can see that we need to find this length. So this length would be equal to S1x, that is 7.40, plus from this point to this point. So this is 2 lambda. That is from one loudness. So from one loudness to the next loudness is 1 lambda. So from first loudness to second loudness is 2 lambda. So here S1y, so S1y is equal to 7.4, that is this distance 7.4 plus 2 lambda, that is 2 lambda. So we get the distance as 9.1 meter. Again, if we just explain, then let me erase this. So basically, we need to find the distance S1y. So S1y, that is S1 from point S1 to point Y. So to find the value of distance, we can first go from S1 to point X, and from S1 to point X, we can go from S1 X to Y. So by covering this distance, here we can see that we covered the distance, that is S1y. So first of all, now here it is given information that S1x is equal to S2x. So S1 to point X is equal to S2 to point X. This length is similar to this length. This is also already given. And here we know that this is the baseline, and from one loudness to one loudness to one loudness. So since these two distances are same, so this distance is also same. That means this distance must be same. So since this distance is 7.40 meter, so this is also 7.40 meter, and we know that S2x is equal to S1x. So S1x must also be 7.40 meter. So first of all, we have found that S1x. Now we know the distance S1x, that is 7.40 meter, and what is x to L or y, that is x to point Y is 2 lambda. So plus 2 lambda. So the total distance, that is this total distance, is 7.40 plus 2 lambda. So 7.40 plus 2 lambda. And what is the value of lambda? So we have given the wavelength as 0.85 meter. So 0.85 meter, substituting the value, we get the distance as 9.1 to two significant figures.